Okay. All right, let's continue. So I hope everyone have this lab case from T. So let's see from, and you guys should be able to run it fine. All right. So let's see from the make file itself. So in this make file, I have make all, which is compile, op, and sim. So for make compile, we have vlog tb.sv and then top.sv, and then I also added plus definition, plus macro definition of plus blocking, and then optimize, we have vop, and then our top top duty, and then dash o for the output, the optimized DU name, and then dash debug, and plus design file. So plus design file will automatically generate the design database that we need. And then for sim, we have vsim, vop minus c, so it's in console mode. Then we do where we run all and then quit f. Then we log the qwave.db signal plus event order. And then we do also svsit random. So on visualizer, we just do visualizer design bin and also qwave.db. So what's happening inside here is we have our top module. It's a very simple test case where we just want to see whether it will have uh, what kind of effect on this race condition. So I have a macro if define non-blocking and also if define blocking. On if define non-blocking, so I have three always block on, and all of this always block is triggering at pos h clock. Then if it's triggering, then the value A is getting the value of A plus 5, and value B here is getting value of A. Value C is getting A plus 5. So let's try running this. First, we start off with blocking block, where we use blocking assignment here. Let's try running this. So on the TB is just a very simple test bench where we instantiate and then we have all the logics declared out, and we toggle the clock every 5 timestamp. So let's run with macro definition blocking. So we just run all, make all. Here I have also printed out the monitor details, but let's look at the visualizer straight. So we'll go into make vis. So here, if you just open it, I don't think you will have the view yet, but what you can do is, let me quit out this thing. All right, from the instance design, instead of adding all the variables one by one, you can actually add all of the variables from the instance here. So add to wave. Then you will be able to see all of the variables added to wave here. And then you can click full zoom so that you can see your full simulation. Then one way of doing it, we can analyze the race condition from this waveform itself. So let's see, because we do not have our macro non-blocking, so it's gray out. So the one that is not gray out, if defined, means we define this blocking macro. So here on every pos h of clock, we will expect A to get A plus 5. And every pos h of clock, we will expect B to get B equals to A. And the third always block, we expect C equals to A plus 5. So let's see on the timestamp 5. So here we are expecting A to change to 5, but it's not changing yet. And then our first change is actually here at timestamp 15, the next pause age clock. So at here we change from A to 5. And then C directly changed to 5 as well because I guess the delta cycle change after A, then it gets to C. So C gets the value of previous A, which is 0, and then it gets plus 5. But value of B changed to 5 as well directly, and it didn't get the value previous of 0. So we can actually analyze further because in our make file, we use QFDB equals to plus signal, and also we added this event order. So right now we can view the event ordering by clicking view and then click event order. So right now, event order is empty. You'll have to add all of the variables to event order. So for example, let's see if we can do it this way. Okay, we cannot add the whole instance, but we can add the variables here. Click all the variables and then right click and then add to event order. Okay, let me maximize this. Okay, now we can see all of the event orders and the timestamp. So at time 0, there's a few delta cycles, so 0 and 1, where we can see event order only tracks the changes here. So it tracks changes where this clock reset A, B, and signal C. So clock change from unknown to 0, and then reset change from unknown to 1 as our initial block. And all of these are done in delta 0. So in delta 1, we change A to 0 and B to 0. And at the same delta cycle, we change also C to 0. Now, when clock age rises here, but there's no changes on signal ABC, but on the next clock age rises, which is a timestamp of 15 nanosecond, at delta 0, clock change from 0 to 1, as we can see here. And then for the next delta, we can see A sends this clock change, so it gets a previous value of A plus 5, and B gets assigned to value of A, and C at the same delta cycle, we get the value of previous A plus 5. So using this event order, you can see all of the same timestamp and also the different delta cycles, and you can see whether this condition is having race or it's not having race. And if you want to have it in a readable way, you can also highlight all of it, and then you change the radix to decimal, and then you sort of enlarge it. You can see the values in decimal as well. So using non-blocking assignment is not actually what we are looking at, and we can actually see there are some races here because for the blocking, for the block of signal B where you get assigned to value A whenever there's a pause age clock. So whenever there's a pause age clock, let's say this pause age clock, and the value A is already changed to change decimal, already changed to 5 to 10, but this value B is still at 5. And C, you keep getting the value of previous A plus 5. So you can see there's actually something weird going on with this waveform. So let's try another wave. Just now we are using this blocking macro definition where we use this blocking assignment. Let's try using non-blocking macro in the makefile. So let's go to the makefile and then At the compound stage, we change the macro definition from blocking to non-blocking. And then the same we run with make all. Then we bring up the debugger. Okay, now we can see the macro definition of blocking is gray out. That means we are not using that blocking macro definition, and now we are using non-blocking macro definition. Let's close this. Now using non-blocking assignment, everything seems to be in a better order, because in the next pause edge of clock, A gets the value of 0 plus 5, and then C also gets the previous value of 5. And then for B, at this pause edge, B still gets the value of previous A. And then on the next one, it's the correct order where B gets the previous value of A, and A gets the previous value of A plus 5, and then C gets the same previous value of A plus 5. So there's no ordering mistake here in non-blocking assignment. So this is a much preferred way of doing the RTL code for race condition. So let's evaluate this event order again. So event order, let's say we are at here. So at time 15 nanosecond, clock will go up. And then there's actually two delta clock cycle where A changed to 5. C also changed to 5, but there's no changes in B because B takes the value of previous A. And then if we go to the next clock, pause edge of clock, then there's also a same delta cycle of A change to 10 and C change to 10, and then B on the second delta cycle, it gets the previous value of 5. So this is for the small test case where we can play around with race condition blocks, and then we can try the event order as well. So you can see to switch on the event order, just to have a highlight again, you can add plus event order in qwave.db, and then you can have this window up. So next, let's try the one from the slide. You guys can try with this. Try having this code in your try having these 3 different codes, and then you can try to see whether does it behave the same, or is it having a different value for a beach ball. You guys can try to code this out in your simulator, and then we can see whether a beach ball does it behave the same from all these 3 different always at block. Okay, we give 5 more minutes, then try to see if anyone got any feedback from for this question. Okay, let's check. So, did anyone have feedback on this? Yep. That's a very good answer. Yeah, thanks for yep, thanks for sharing. So, if anyone else that haven't tried it out yet, let's see from here. So I've tried to mimic the situation and also make the monitor for each, and then using if def to assign the instantiation of three different logic block. So if I do if def one, so I do compile if def one, and then I do make all. So let's just quickly go through this because it shouldn't be a lot of issue here. So whenever there's a clock edge and then stripes equals to one, and then colors equals to one, beach ball and bouncy haven't changed yet. But at clock two, this bouncy changed to one, and then the rest the patterns is like this. And if we change it to plus define two, make all. So the pattern changes again, and this time, whenever stripes and colors change to one, beach ball and bouncy, they already changed to one. So there's a difference between this non-blocking assignment and blocking assignment. All right. So that's all for the labs on race condition. So right now, let me share with you one of the very good video on race condition that my colleague did. So let's get some time and let's view this video because I feel there's a lot of things we can learn from this video as well. And if there's any question, don't hesitate to stop me. Then we'll discuss on the video materials as well. Let's see. Let me share this. Share this one. Share some.
Hello everyone. Welcome to today's expert series webinar on strategies for debugging race conditions in functional simulation. Here is our agenda for today's webinar. First, we will discuss what a race condition is.
So let me know if you cannot hear the audio from the video. And yeah, in the chat, if you can hear, then that's cool.
I hear.
Then,
Yeah, you can hear.
we will go over some basics of event-based simulation, followed by a few examples through which we will further understand how event ordering works among different scheduling regions. Then we will discuss different manifestations of race conditions. Then we will get into the more interesting part where we will use QuestaSim and Visualizer to debug a race condition. Then we will explore how race detection can be automated with the help of some new Questa and Visualizer features. We will wrap up with a quick summary. So with that, let's get started. The first question is, what is a race condition? It is a situation where the outcome depends on the order of execution of events, where the order of execution is not guaranteed. In other words, a situation where the outcome is not consistent. And this transient nature makes debugging race conditions more difficult. To better understand race conditions in the context of functional simulation, first, we have to review some of the basics of event-based simulation. In your design and test bench, there are concurrently scheduled processes such as always blocks, initial blocks, continuous assigned statements, etc. These processes generate events that get scheduled either in the current time slot, starting from time 0, or in a future time slot. The simulation proceeds by executing and removing all these events in the current time slot before moving on to the next non-empty time slot. In my code snippet here, you can see two initial blocks. The first initial block is at line 5, and it has a blocking assignment after a delay of 2 units. Therefore, it schedules an update event to update x to a value of 4 at time t equals 2. In parallel to the first initial block, I have another initial block at line 9 that has a non-blocking assignment with an intra-assignment delay of 2 units. So this NBA schedules another update event at t equals 2. So at t equals 2, we have two events. One is the NBA that we just discussed, and another is the blocking assignment. So the question is, when there are multiple events scheduled for the same time slot, in what order should these be evaluated? For some cases, the evaluation has a specific order, but in other cases, there is no guaranteed order. Race conditions happen when we make incorrect assumptions about event ordering. In this example, at the end of time slot 2, x will have a value of 3 because even though there are two update events, the blocking assignment gets scheduled in what is known as active region, and the non-blocking assignment gets scheduled in another region called NBA region. According to the System Verilog Language Reference Manual, NBA region is processed after active region. So the NBA wins in this case, and x gets 3. In addition to blocking and non-blocking assignments, System Verilog has many other language constructs that can schedule events in many other event scheduling regions. The diagram on the left shows different event scheduling regions supported in System Verilog. All the events scheduled in a time slot will fall under one of these scheduling regions. When the simulator processes events in the time slot, it goes through these regions in an ordered manner as shown in this diagram. Going back to our previous example, the active region associated with the blocking assignment comes first, and the NBA region associated with the non-blocking assignment comes after that. Let's quickly go through these event scheduling regions. The area marked between these two dotted lines represent a time slot. The regions marked in oval shape are the PLI regions, and we are going to skip those because those are not really interesting. Here you can see the entry to the current time slot at the top left corner. And the first region that will be processed is the preponed region. This region is associated with sampling expressions for concurrent assertions or variables referenced in an always FF procedure in a checker. Since this happens first, you get a nice stable value to evaluate your assertions. The next region is the active region. There are many events associated with this region. For example, the blocking assignments, continuous assignments, dog display calls, evaluation of inputs and updating the outputs of primitives, evaluation of arches of NBA. You can think of non-blocking assignments as a two-step assignment. First, the arches of the NBA is evaluated in the active region, and then the LHS of the NBA is updated in another region called NBA region down here. Next is the inactive region. If you have ever used a #0 delay to solve a race condition, it worked most likely because it delayed that assignment by pushing it to this inactive region. Next is the NBA region. As we discussed, updating the LHS of a non-blocking assignment happens here. You can also see that there are arrow marks coming from these regions and going back to the top, indicating that this is an iterative process. For example, evaluation of NBAs in NBA region may trigger events in the active region like another always block. If this iteration doesn't settle, you may encounter a zero delay loop. Next is the observed region associated with the evaluation of concurrent assertions. I put the next few regions in the same group because if you pay attention, you can see that this group is similar to this group at the top. The regions in this group have a re prefix and they are associated with assignments in a checker, program blocks, action blocks, or pass fail blocks of concurrent assertions. Just like how you can have procedural blocking or non blocking assignments associated with this region, the first region, you can also have those types of assignments in the action blocks of concurrent assertion. So those events are processed in their corresponding region with the re prefix. Here also, it is an iterative process. And finally, we have the postpone region where calls like $monitor and $strobe are evaluated so that they give the final settled value in that time slot. After this, we move to the next time slot where we will repeat this whole process all over again, starting from the preponed region. Let's review this example. Here I have two always blocks, one at line 11 and another one at line 15. And both of these are sensitive to the passage of the clock. So both of these will be triggered at the same time slot. But we cannot assume that one always block will be executed first, followed by the other. And inside these always blocks, I have blocking assignments here. The first one assigns X with a value of 3, and the second one assigns that X to Y. But the problem here is that both these are blocking assignments and they are evaluated in the active region. And also, we are not sure which always block will be executed first. If the first always block gets executed first and X equals 3 happens first, then Y will get the updated value of 3. So X and Y will be 3. But if the second always block gets executed first, Y will get the previous value of X, and then X will be updated to value 3. So this is one scenario where we cannot guarantee an event order. So this is another example that shows not everything is arbitrary. Here I have an initial block at line 5, and it has a non-blocking assignment with an intra-assignment delay of 10 units. And then I have another initial block at line 8. It has a $display statement that prints the value of X, but it is delayed by 10 units. And then I have another initial block and it has a $monitor that prints the value of X. Since we know that X will be changing after 10 time units, this $monitor will also be executed at that point. So we have three potential things that can happen when time t equals 10. But these are evaluated in a certain order. First, we have the $display after 10 time units, and that is evaluated in the active region. So that happens first, and it prints the value of X from the previous time slot. And here X is bit, so initial value of 0. And then the non-blocking assignment updates its LHS in the NBA region. So at that point, X will be updated to value 3. And then the $monitor will be evaluated because that's processed in the postponed region. And when $monitor prints the value of X, the non-blocking assignment has already happened. So $monitor will be printing the updated value of X, which is 3. Next, we will discuss different manifestations of race conditions. First of all, it is hard to conclude if something is a race condition or not without actually analyzing that in detail. The following are some of the situations that may involve a race condition, but most of these can happen due to other reasons as well. So the first one is when you encounter unexpected signal transitions that are hard to explain. Scenarios like signals are skipping a clock edge or signals are staying unchanged for too long. This type of behavior can also happen due to a tool defect. The next one is when rerunning simulations using the same code base, but with different simulator options, it gives different results. Another situation is when you encounter functional differences between different simulators or between different versions of the same simulator. There can be many reasons for this difference. Randomization difference can be a big factor here, but a newly exposed race condition can also be one of the reasons. The last and the least obvious situation is when you start seeing functional differences after making a code change. Again, there can be so many causes for this, but the point here is that just reordering or adding or removing procedural blocks can be sufficient enough to change the event ordering and expose a race condition. These can expose a race condition because events that need not be scheduled in a certain order can change their ordering when you change some specific simulator options or your source code. Now we will switch to a demo in which we will explore how QuestAsym and Visualizer can help in debugging race conditions. I'm going to use a simple test case for this demo because the point is to show various debugging techniques. Here, I have a test that is failing due to an assertion error, and this is the first error message from this assertion. To debug this in Visualizer, I am going to enable Visualizer Q-wave dumping. In the top window, you can see the script that I am using for this test. It uses a three-step flow, vlog, vopt, and then vsim. To enable Visualizer wave dumping, first we have to add two options to the vopt command, which is the optimization phase. First, I will add the option -design file. This option will generate a file called design bin that will contain the information about the design. Then I will add the option -debug, and this will make sure that the optimization engine enables the infrastructure required to do wave dumping during simulation. Now we will have to add a new option called -qwavedb to the vsim command. This option will tell the simulator to generate the wave dump file. Along with -qwavedb, you can also specify what type of objects you would like to be dumped to the wave dump file. Here I will just specify plus signals. This option will dump all the RTL signals. Then I will add another option called event order to make sure that the event order information is preserved. For normal debugging, you don't need plus event order, and it may even slow down your simulation. But here, we know that we will be debugging a race condition, so we need the event order information for that. Now I will save this script and rerun it. If you check the generated files, you can see two new files, the design file and the wavedump file with the name qwave.db. Now we will load these two into Visualizer. For that, you can use the command Visualizer followed by the design file, and then you specify the wavedump file with the wave file option. Now we will just go back and check the assertion error message in detail. According to the error message, it is expecting the value of S1 to be 5, but the actual value of S1 is 10. And then the error message is also saying that the assertion got fired at simulation time 15 nanosecond. So I will just go back to Visualizer and set the simulation time as 15. You can see that all the windows got synced to simulation time 15. Okay, going back to the error message once again. The assertion is coming from this particular scope and this file and line number 31. I'm going to use the Visualizer design window search feature and paste the value of the scope I copied and directly go to that scope. Okay, we are in the correct scope and scrolling down. And here is the assertion error message at line 31. Looks like it is asserting a property called P1. and it is defined here at line 26. The property says that at every passage of the clock, scene must be equal to S1 plus 5. Note that the assertion message is already using the sampled values. From the value tooltip, we can see that at this point, scene is changing from 10 to 15, and therefore the sampled value must have been 10. Similarly, S1 is also changing from 10 to 15 with the same sampled value of 10. But we expect S1 to have a sampled value of 5 at this point. So we will have to chase this S1 signal, but first I will add the clock and these two signals, scene and S1, to the wave window. So that will enable us to check how they are changing over time. So here is my primary cursor at time 15 nanosecond. Looks like these two signals have the same value for the most part. To check if there is any divergence between these two signals, we can do a quick compare by selecting these two and then right click, compare, simple. Now we can use these two buttons to check if there are any differences. First, let's check if there are any differences in a future time. Specified edge not found here at the left corner. So let's check if there are any differences in the past by clicking on this button. Oh, looks like there are some differences until 5 nanosecond. Comparison differences are denoted by this red color. So something is going wrong at this point in time. So we will have to trace the driver of this S1 signal. For that, first I will enable active driver tracing from the toolbar. Then right click on S1 and show drivers. Okay, we have a few changes here. On the right side, we can see that there is a new drivers window. It lists all the drivers and their details. The active column at the end indicates whether a given driver is actively driving at this point in simulation time. Without active driver tracing enabled, you might have seen a question mark here instead of Y or N. Looks like the driver at line 21 is the active driver. So let's double click on that and see what is it doing. If you hover over these signals, you can see that scene is becoming 10 at this point, which is the correct value. And we are expecting S1 to be 5 less than scene. But S1 is directly jumping from 0 to 10 instead of 0 to 5. So most likely S1 might have gotten the new value of scene, which is 10, instead of its old value of 5. This is where we can use the event order window to analyze the order in which these events are happening. To do that, I'm going to select clock, scene, and S1, then right click and add to event order. Okay, you can see the event order window on the right side. In the left section of the event order window, you can see the simulation time going from top to bottom. You can move forward and backward in time by clicking on the appropriate time slot, and it will sync all the windows to that particular simulation time. The second delta column shows different delta events within a given time slot. These delta events are not a one-on-one mapping to the SV scheduling regions, but these delta events help us understand the order in which different signals are changing their value in the given time slot. Then the right section has all the signals we added to the event order window, and it shows the value of the signals in a given delta in a tabular format. The hyphen indicates that the value did not change in that particular delta. So the time slot 5 nanosecond has 3 rows, one for delta 0 and two for delta 1. The clock changed to 1 in delta 0, and then the Cin changed to 10 in delta 1, and then S1 changed to 10. Now if we scroll up to see the previous time slot, which is time 0, you can see that the final value of Cin was 5 in time slot 0. Since we expect S1 to have a value of 5 in 5 nanosecond, we expect S1 to read the final value from time slot 0, which is this. This value must have gone here. Instead, it read the updated value of 10 from the same 5 nanosecond time slot. To find out why this is happening, we will have to trace the drivers of Cin further. So let's right click on Cin and select Show Drivers. Looks like the driver at line 8 is the active driver at this point. And here is line 8. So Cout is driving Cin, which was used in the RHS of the previous NBA. Cout is written by a blocking assignment here. And at the same time, one of the receivers of Cout is RHS of an NBA, the previous NBA we discussed. So we have a problem here. Going back to our discussion on scheduling regions, blocking assignments, like the Cout here, are scheduled in the active region. At the same time, evaluating RHS of an NBA, like here, is also done in active region. Active events can be taken off from the active region and processed in any order. The coding style here made an incorrect assumption that the evaluation of RHS of the NBA should happen first, followed by the blocking assignment to the Cout. So that is our race condition. You probably already know how to fix this. Let's go back to our blocking assignment here. As you can see here, we are trying to model a counter that gets incremented by 5 in every passage of the clock. So to model sequential logic, the best practice is to use non-blocking assignments. If I change this assignment to a non-blocking assignment, first, the original NBA will read the old value of Cout because it happens first in the active region. After that, the Cout will be updated to its new value because that happens in a later NBA region. Now I will exit from Visualizer, then go back to the blocking assignment and change it to a non-blocking assignment. Save that file and I will rerun the test. Okay, we do not see any assertions now. That's good. I will launch Visualizer once again. Okay, we still have all the signals. I will just select these and add them to the event order window. And you can see that if you check 5 nanosecond, S1 is actually getting the previous value of Cin as we expect. So that resolved our race condition. The next question is, can we make things easier by automatically detecting these race conditions? The answer is yes. There are some new features in QuestaSim that can automatically detect race conditions, generate a report of these race conditions, and also dump the same information to the QFDB file to make it easier to review these race conditions in Visualizer Debugger. To enable race condition report, we will need to add a new option to the vopt command. And the option is detect races. This option will automatically detect race conditions and generate text-based reports of the detected race conditions. In addition to this, you can specify comma viz to dump information about the detected race conditions to the visualizer QADB file. Now I will quickly go back to the source code and reintroduce the race condition, save it, and save the run script. And then I will just rerun the script. Okay, the race conditions are back. Now, if you check the newly generated files, you can see three files associated with the race detection: the underscore races, then racedetect.txt, then racedetectunique.txt. Let's open the file racedetect.unique.txt. This report contains all the unique races that got detected during the simulation. If there were multiple occurrences of the same race condition at different points in simulation time, you will see the first occurrence of that race condition. So here we have one race condition reported, and the report says that the race condition happened at 5 nanosecond, and this is the signal associated with the race condition. Then it says that there were 20 occurrences of this race condition. After that, you can see more information about the nature of race condition. So here it says that it was a write read race condition. And the write happened in this scope, this always block, the sub2.sv file, and line number 8. Let's quickly open this file, which is here, and check the line number 8. So this is the blocking assignment that we previously debugged. And then there is another read operation, and it's happening in this scope, sub1.sv file, and line number 21. So let's open that and go to line number 21. So that is the non-blocking assignment, and we are reading the written value on the RHS of the NBA. So this is the same race condition that we previously manually debugged. Also note that the race detection is disabled for time 0 by default. In case you want to enable it, you can use this particular command when you run the simulation. Make sure that you put this command before the run command. For example, it should come before your run all command. Now let's open the next report, racedetect.txt. This file contains all the races that got detected during the simulation. Here you will see multiple occurrences of the same race, but at different simulation time. So here we will likely see 20 such entries associated with the original race condition. And finally, we have one more report, the underscore races. This is a simple report that just lists all the signals associated with the race condition. So that is all about text-based race detection. Now let's check how Visualizer can make this even better by providing an interactive environment to review these race conditions. I will reload the newly generated QFDB file using the exact same Visualizer command. Since we specified vis with the detect races option, information about all the detected race conditions got automatically dumped to the QFDB file. And those are now available in the Visualizer message viewer window. So let's open the message viewer window from the view menu. In this window, you can see all the detected race conditions. We can further filter the race condition based on any of these filter boxes. Or you can filter based on the simulation time. You can also change the sort order. If you want, you can show more information about each of these race conditions by adding more columns. For example, I did a right click and then you can select additional columns. Let's select category, line number, and the scope associated with the race condition. You can see the newly added columns. Now, if you want to filter only the messages associated with the race condition, you can use the filter on this category and you can select the races checkbox. This will be useful in big test cases because there can be many messages already in the message viewer, for example, the UVM messages. You can also group these to make analysis easier. For example, if we want to see race conditions grouped by their scope, we can click on this group button and select the column you want to use for grouping and click on this right arrow and hit OK. Now you can see that the race conditions got grouped based on their scope. Similarly, you can group based on any of the other columns. If you want to check the details of a specific race condition, you can just double click on the required race condition, and that will take you to the correct scope, line number, and the simulation time associated with the race condition. To summarize today's webinar, we started off by defining what a race condition is, followed by a detailed discussion on different event scheduling regions. Then we further expanded on event scheduling regions with the help of a few examples. Then we discussed manifestations of race conditions. After that, we used QuestAsim and Visualizer to debug a race condition using driver tracing and event order window. And finally, we explored how the new automatic race detection feature can make debugging race conditions easier and faster. And that is all I have for today's webinar. I hope you learned something new today, and thanks for attending.
Yep. That is from one of my colleague in North American region. So it's very good at debugging race condition. I hope you guys managed to also learn some debugging strategies from Jessel. So it's how about let's take a 15 minutes break since it has been an hour already, and then we'll come back at 2:50. Yep, 2:50. Then we'll continue later after the break. Will be on coverage collection.
Okay, okay. Thank you.
Yep, yep. Thank you.